Well, first of all, I'd like to thank the organizers for organizing this wonderful conference in this lovely location. Thank you for inviting me to speak. So I'm going to be talking about some joint work with Trevino. And so we're just still in progress, ongoing. So the topic that we've been thinking about is flat surfaces that are of infinite type but finite area. And in particular, how do we construct such surfaces? How do we describe them? What are their properties? Is there some sort of way in which we can view infinite surfaces that sort of allows us to talk about these things in a sort of easy to manage manner? So to that end, I'm going to start off by talking about something which at first glance may seem completely unrelated. I want to start by talking about the dynamical system. This is the dynamical. This goes under many names. You might have heard of it as the infinite adding machine, many different ones. But I'm going to present it in a number of different ways. My first is going to be sort of a symbolic definition. The space for my system is going to be infinite sequences of zeros and ones. And my transformation, t, on x, is given by addition of 1 in base 2 with carry to the right. So for example, I'm going to put a decimal point just to mark the beginning of my infinite sequence. I could do a sequence that maybe starts 1, 0, 0, 1, 0, etc. would be an element of my space. And the way the map works, if I apply my map t to this point, I add 1 to the first digit, and in base 2, and I carry to the right. So if I add 1, 1 plus 1 is 0 with a carry to the right. So this would be 0.0, 1, 0, 1, 0, etc. So some properties of this system. T is uniquely ergodic. And the natural measure is the one that comes from cylinder sets on these sequences. It's not weak mixing. And there's a lot in the literature that's been very well studied. You've likely seen it before. Now I want to start with a different incarnation of the dyadic odometer. I want to define a map, say phi, that goes from the space x to the unit interval, which I'm going to note by I, defined by phi of x. I'm thinking of x as being my infinite sequence, say x1, x2, x3, as the sum over all of the digits, sum over I, of xi times 2 to the minus I. So this map is bijective, except at a countable set of points, those points which sort of have a non-unique decimal expansion base 2. And so it maps bijectively onto maps, say, outside countable sets. My maps, say phi is a bijection onto its image, which I'm going to call J, which is the interval minus the image of those points. It's a countable set. So we can now look at the conjugation of this map, of the T map, via phi. So we can look at the map, say R, which is defined on J, gives you other points in J, given by R of x equals, so I'm starting in J, so I'm going to pull it back by phi inverse, then I'm going to do this T And this map R is just the restriction to my set J of, I'm going to say R tilde, actually defined on the unit interval, I to I. And R tilde has a very nice description. Say R tilde of 1 minus 2 to the minus n plus x equals 2 to the minus n plus 1, parentheses, plus x for 2 to the minus n less than x less than 2 to the minus n plus 1. So what's this look like? I don't know, it's just the point, there's some nice explicit formula. But if I draw the graph of this, here's 0, here's 1. The graph takes the first half interval, maps it like that. Now we have another. It goes on and on. All right, so these lines right here, which maybe I'll draw in a different color. It's orange. This is the graph of that map. As you can see, it's an infinite interval exchange map. In this form, it's sometimes called a Van der Waals map. As you can see, it's just another version of the diagonal. And also it's an infinite IET. Okay. Now I'm going to get yet another way of looking at this map, or constructing it. We can construct this via the method of cutting and stacking. Okay. Cutting and stacking is a method of describing a map as the limit of a sequence of maps. So I'm going to construct the map T. I refer to it as R over here, but now I'm going to call it T. They're really all the same. T is the limit of a sequence of maps, which I'll call T1, T2, T3, etc., which have the following property. Their domains grow as we go farther out the sequence, and the restriction of one map to the domain of the previous map agrees with the previous map. So write that down. So such that if I look at the Tnth map, I restrict it to the domain of the Tn minus 1 map. It agrees with the Tn minus 1 map. And the union of all these domains, so domain of Tn, is the whole unit interval. Well, actually, we can open bracket on the other end. So the construction involves columns. My columns are denoted by C. I'm going to start with C0. C0, I'm just going to take to be the unit interval, 0 to 1. C1, oh, and there's sort of a T0, which is the transformation which is not defined anywhere. C1, we're going to cut this interval in half. We're going to stack the bottom half under the top half, left half under the right half. So now we have 0 to 1 half, 1 half to 1. So this is my column C1, and I'm going to define a map T1 where the domain of this map is 0 to 1 minus 2 to the minus 1. In other words, 0 to a half. And the way this map is defined is it just takes a point on this bottom interval, which is where the map is defined, and it maps it to the point that's directly above it. To form C3, my next column, I'm going to cut this column in half, stack the left half underneath the right half. So now I have 4 little intervals, which are each 1/4 wide. So I have 0 to a quarter. Above it, I have 1 half to 3/4. Then this half goes under this half, so we have 1/4 to 1 half. And then we have 3/4 to 1. My map, T2, is going to function exactly the same way, and that for any point I pick that's not on the top level, it's just going to map that point to the point immediately above it in my column. So T2, the domain of T2 is everything except this top level. So T2, it goes from 0 to everything but the top level, which is 1 minus 2 to the minus 2, to 1. To the unit interval. And inductively, if we can continue this process, we have some column with a bunch of levels, Cn, and it has a domain. To form the column Cn plus 1, we cut Cn in half. We stack the left half under the right half. So here's this left half, and the right half. And T, this is n plus 1, is defined the same way. Each point just moves the point directly above it, and is defined everywhere except this top level. So that means it's defined on everything except 1 minus 2 to the minus n plus 1. Maps to I. So the sequence of maps we construct in this way satisfies these properties that as we keep going, if we go far enough out, the domains eventually include the whole unit interval, open bracket on the right-hand side. And each one just is an extension of the previous map. Okay. So now, I'll raise my first dyadic odometer representation. I'm going to draw the surface which Anya presented, this was yesterday, the surface due to Chamanara. So this surface, to construct it, we start with a square, and there's various edge identifications on the top and bottom of the square. So we cut the square into intervals along the top and sides as such. And this is an infinite. Each time is half as big as the previous time. And the way we glue the top is we call this segment A, and glue it to this segment A, B, B, C, C, etc. And maybe, I don't know, X, X, Y, Y, Z, Z, and some more letters. So this is the Chamanara surface, right here, which was sort of one of the first examples of an infinite type finite area translation surface. Now, if you notice, let's look, just ignore the identifications on the left and right hand side. Just look at the identification on the top to the bottom. 0 to 1/2 is mapped to 1/2 to 1. Okay, that's this picture. 0 to 1/2 is mapped to 1/2 to 1. This interval is mapped here, and it corresponds to this line segment right here, and so on. And so you can see this is actually just in the vertical direction. It's a suspension of the dyadic odometer. So what is it? So if we have a point x, 1, I'm thinking of this as being the origin right here. The square is 1 unit tall. It is identified to t of x, comma 0, where t is this dyadic odometer. So this is the top to bottom identification. And then we have the left to right is, again, just the suspension of the same dyadic odometer. So it's 1, comma y is identified to 0, comma t of y. This is all sort of the introduction, by the way. This is an example which is going to illustrate a sort of more general construction. Okay, so that's the Chamanara surface, which we've seen is secretly hiding the dyadic odometer. And finally, I just want to make one more comment about the dyadic odometer, which is how to represent this cutting and stacking process using a Bratteli diagram. direction. And, okay, I'm claiming this represents like the dyadic odometer. How does this tell us what to do? Is there a question?
No.
No.
This is next.
Okay. Let's see what I was going to say. Right. So the Bratteli diagram is we're going to interpret as instructions for doing a cutting and stacking transformation. Each vertex we're going to think of as representing a column in the cutting and stacking construction. Each vertex corresponds to a column, and in particular, the V0 level vertex corresponds to the C0 column. V1 vertex corresponds to the C1 column, and the number of edges which leave a vertex corresponds to the number of pieces which you cut that tower into. So in this example, we cut each tower into 2 pieces, so thus there are 2 edges coming out of the vertex. Edges which leave a vertex is related to the number of pieces you cut that tower into. And if you look at the edges which come into a vertex, those are the pieces which you stack to form the next tower. We'll say edges which enter a vertex tell you which pieces to stack. Pieces of the previous level towers there's one other thing I should maybe add to this diagram. I'm going to add a weight. I'm going to write 1/2 on each of these edges. What this means is that when I cut into my 2 pieces, this piece should be 1/2 the width of the column, as should this. So these are weights. So I really want to erase. I'm just going to write. You have to have a weight function on the edges. And also, if you notice, there's an order on the way the edges leave and enter each vertex. I'm thinking of the left-hand edge emerging from a vertex as corresponding to the left-hand part of a column, and the right-hand, the edge coming out on the right-hand side corresponds to the right piece of each column. The order that they come into this vertex, the left comes in before the right, so that I stack the left under the right. Okay.
So these are embedded directed graphs, they're not just abstract directed
Right, they're embedded directed graphs. Or you can think of them as coming with a 2 partial orders. Well, yeah. Okay. So let me just that's the end of my sort of example spiel of the dyadic odometer, but I want to make some comments about the sort of philosophy of this. So what are we doing? We're talking about how to construct these surfaces. So constructing, apparently can't spell, constructing infinite type, finite area surfaces. So the sort of philosophy here is we could start with a Bratteli diagram, which tells us our instructions for cutting and stacking. And we need to have some height and width data on these columns. And that data, the width data, has to be compatible with the way we stack the columns. So I'm just going to say some compatible width and height data. We then this as instructions for cutting and stacking, and then we take that transformation and we just construct a suspension over the unit interval. Suspend over unit interval. And voila, we have this nice description of a large class of infinite type surfaces. Right, so let me make a few additional comments about this. Yeah.
How do you identify the sides?
How do you identify the sides? I will get to that later. The answer is you suspend another cutting and stacking transformation on the sides. And exactly the way those two fit together will be something I talk about in just a minute. Okay, so a couple remarks. If we look at the vertical flow on a surface, the dynamics of that vertical flow exactly agree with the dynamics of the map which we're suspending. So I'll say the dynamics of the vertical translation flow on the surface are exactly the same dynamics as those on the suspended interval. And this is wonderful because many people have put a great deal of effort into understanding cutting and stacking transformations. And this allows us to construct surfaces with, in which the vertical flow acts in desired ways. So in particular, this gives us some new phenomena not observed in finite translation surfaces. So not in finite type translation surfaces. So for example, using an appropriate map, you can construct surfaces whose flows in this vertical direction are strong mixing. Strong mixing. I'm adding the strong as opposed to weak, but for this mixing, strong mixing. I'm going to say surfaces. What I mean by that is the vertical flow on that surface is mixing.
And you claim that doesn't happen for compact case as well.
Right. This is truly an infinite type.
Oh.
This is something different in this infinite type surface world. Also, we can construct surfaces where this flow has positive topological entropy.
Whoa.
Which again does not occur in the finite compact case. And in fact, these things are, in whatever the appropriate sense is, quite common. Okay. So now I'm going to talk a little bit more of the details of this construction, and then after that, I'm going to talk about how to apply the theorem of Rodrigo to show that this vertical flow is actually uniquely ergodic in a large class of examples.
Can I ask a question before you continue? Because if you want to build surfaces with those two properties, do you control the accumulation of singularity points on the surface?
Do you control the what?
The singularity that appear on the surface, because you want them to be discrete and all that.
Right, so
There's only one.
constructed in this way, using a square, all of the singularities that you get will have infinite, sort of infinite cone angle. We're calling the talk channeling Anya right here. I think they may be wild singularities as well. Yeah.
Yeah, I can answer that. It's only one singularity and it's wild.
In this case, one.
For
Just one singularity. Yeah, and I guess for all there will be just one singularity.
I'm not, you're probably right.
I know.
As I said,
For
this is
strong
not
mixing?
work. We haven't figured out all of the sort of details yet. But,
It's going to be the strong mixing material field. You
Can
can
you,
tell me once.
I know you mentioned it, can you remind me
Why?
how that labels on the edges come into play? I mean,
yeah, let me actually, I'm going to do another example right now, and I think that will clarify things. So I'm just going to draw of sort of a fake Bratteli diagram. Let's say, I was trying to come up with an example beforehand that would sort of elucidate the construction. So this is some little finite segments of a Bratteli diagram. We call this V0. These are the level V1 vertices, level V2 vertices. And I need to put some weight functions on these edges. My weight functions, at least for this little segment, are going to be 3/8, 3/8, and I wrote 3/8, but whatever that is, that adds up to be 1 quarter. 1 quarter. 1/3, 2/3, and 1. So what does this mean? V0 we interpret to be the unit interval. Now this says cut, in fact there are 3 edges coming out, means cut it into 3 pieces so that the relative widths of these pieces are 3/8, 3/8, and 1 quarter.
So don't you want the weights to add up to what?
Coming out of each vertex.
Coming out of each vertex, they add up to 1. So now I'm going to form the sort of level 1 columns. This says, so I'm looking at this vertex right here. There are 2 edges coming into it, and those 2 edges correspond to these 2 pieces. This piece, the leftmost piece, is the leftmost piece when it exits, so that's this one. And the right-hand one is the rightmost piece of the way it exits. So the sort of level C1 column would consist of this interval, 0 to 3/8, 3/8 to 6/8. That's 1 column. And in fact, there's 2 towers that form this stage. And then over here, we just have 6/8 to 1. So this picture corresponds to this level. To form the next level, there are 2 vertices, so there will again be 2 towers. So this says there are 2 edges that exit this vertex. So that means I cut this tower into 2 pieces, and the relative widths are 1/3 and 2/3. So I'm not going to do the arithmetic, but this is 1/3 the width of that, or 1/3 and 2/3. And then this one, we don't cut at all because there's a single edge coming out of it. So to form this level column, this part becomes this left vertex. And then to form the right vertex, the edges that come into it, of course, these 2 corresponds to this sub-tower and this sub-tower. And they're stacked with this one underneath this one. So we have, I should probably use colors or something. Orange, green. So we have orange, the green, and then yellow.
And that yellow one is longer than the orange and green.
No, the yellow one is the same length as the orange and green, assuming I've done my arithmetic correctly. I was choosing these numbers so that the widths would add up to be the same width.
So there's a restriction on what you can put on the edges.
Yeah, so earlier I wrote something about compatible weights. So the weight function you choose needs to be work compatibly with the diagram that you choose. Right, so I guess maybe I don't need to write down all the things I was going to write, but I'll just sort of verbally say them. So a Bratteli diagram, it's an infinite directed graph where the vertices and edges are separated into these different disjoint levels. And we're assigning this compatible weight function. That means that when you stack 2 things, they have the same width. Any periodic Bratteli diagram admits a compatible weight function. And though we haven't really worked at all the details, we believe that any Bratteli diagram admits a compatible weight function, though the details are still to come. And yeah, I think that's maybe all I'm going to say right now, other than this is not a true Bratteli diagram because we have this additional data. We have an order on the edges, the embedding into the plane that Josh was mentioning. We have this weight function, and we're actually going to find it useful to consider not only diagrams that start from V0, V1, V2, but they're in fact bi-infinite. So we're going to be looking at bi-infinite, I'll say ordered. We haven't really settled on the names, but ordered referring to the way the edges exit and enter each vertex, ordered, compatibly weighted, Bratteli diagrams. Okay, so now why am I saying by infinite? I'm totally switching to by infinite as opposed to just single-sided infinite. By infinite. Well, imagine you have your square, and there's some Bratteli diagram that gives you the identifications on the top and bottom. So here's my top to bottom diagram. So I don't know what it looks like. Maybe it looks like, I'm just drawing something at random really, but it does something. And that gives you the top to bottom. You have another one which gives you the identifications on the side. And the direction here is going down, so this is V0. Say left, right, identifications. And just bear with me for a minute, because instead of writing it going down, I'm going to write it going up. Whatever it does. It goes in the upwards direction. So I want to consider how the side identifications change if I do the cutting and stacking move indicated by this first level of edges. This first level of edges says cut your thing into 3 pieces with whatever the appropriate weights are and stack them. So now I have something that's a third as tall, third as wide, 3 times as tall. I'm going to label my edges, A, B, and then this is whatever intervals to be whatever the thing is. So A is on the bottom, or sorry, this, I'll say left, middle, right. So I have left, middle, right. So this edge is here. This edge is here, whatever the thing is. Then we have the A identification is going here, A to A. The B is going B to B. So now, this is obviously stretched. It's no longer a square. But if we just ignore that fact for a minute, imagine rescaling by the appropriate amount so that it's a square again. What would the Bratteli diagram that gives you the left-right identifications look like? Well, it looks like the previous one, except we added this picture to the bottom of it. So when we went from here to here, so I'll use orange to indicate my new surface. If I call this V0, starting from right here, that's this surface. And now the left-right identifications have changed. And the way they changed is we've taken this piece right here and we've added it on to the diagram that gives you the left-right identifications. So the sort of forwards sequence for the top-bottom, if you look in your history, that's reflected in the left-right identifications. So the reason I drew this one going down and this one going up is because I really actually want to combine them into a bi-infinite picture. So here's V0 going down. This gives you the top-bottom identifications. V1 going up. I'm just sort of moving this to right here. We have whatever it is. Here's my V-1 level. So you can see that by doing one of these actions, moving V0, the result is you're just sort of transferring what your starting point is on here. And you're stretching your surface in some way. So we've talked, a lot of people talked about the geodesic flow. So this stretched version, which corresponds to sort of shifting where the 0 level of your bi-infinite diagram, what that corresponds to, as we saw, is like stretching, making your thing taller and narrower. And the matrices that would sort of undo this change, get us back to a square again, are those that are given by matrices of this form. So what we can see is that if we were to apply this matrix to this square, or rather tall skinny rectangle, with the appropriate value of t, we would again end up back in a square. And part of our assumption, which I think I've erased now, is that we want the V0 to be 1 unit wide. The sum of the widths of the V0 level columns to be 1. We also want the area to be 1. Right. So what does this mean? This means that associated with each level, say k, of your bi-infinite Bratteli diagram, there is some time, which I'll say tk, there exists a time, t sub k, which takes whatever your object is and stretches it so that it, the horizontal distance is again 1. So let's see. Time tk such that gtk applied to the surface, which we get by shifting down k steps, gives you something 1 unit wide, gives a V0 level, which is 1 unit wide. So just a notation. Let me see if I can. So associated to the vertex, I'll say V in my kth level vertices. There is a height and a width data for the column that represents. There's a subnotation of that L, VK, L for length, but it's actually on width of the column corresponding to that vertex. So this is the cutting and stacking column corresponding to that vertex. And there's a height, HVK, which is simply the number of levels in that column. Height of that column. So if you apply this renormalization operator, the GTK, we're moving from our very stretched thing to something else. And we can compute how those heights and widths change. We can write that, losing my notation, but I'm going to write the new height, HKVR, is going to be just e to the minus tk times my original height, the height in my diagram before I moved it, and the new length, LVK, sorry, my V's are at the top. No. It's going to be e to the positive tk times lvk. Right. So as I mentioned, if your diagram is periodic, this gt is an element of the V truth of that surface. That is, it's a shear which gives you back your original surface. This was why Anya referred to the Trevino surface as the baker's construction. And I'm running out of time, but I'm going to quickly tell you about the way Rodrigo's magic theorem applies to this type of construction. So, on Monday, Rodrigo gave a lecture, which some of you are here for. The main theorem was that he gave conditions which guaranteed that the vertical flow on a infinite type finite area surface is uniquely ergodic. So he gave conditions on the geometry of infinite type or finite type, infinite type finite surfaces which guaranteed that the flow in the vertical direction on that surface is uniquely ergodic. The vertical flow on that surface is uniquely ergodic. And his technique was similar to that of, in spirit, to Mazur's criterion, which is that if you control the rate at which your surface degenerates, if that's sort of appropriately bounded, that tells you something about recurrence in moduli space and about the ergodicity of the flow on the surface. I'm not going to write out his entire theorem, but if you I want to recall the ingredients that went into it. He can correct me as I go. We wanted to control the rate at which the diameter of the surfaces. Oh, let me back up a step. He started with a surface S, and he had a sequence of subsets, say S1, S2, S3, subsets of S, which eventually expand to be your entire surface. And these subsets had to stay a certain distance away from the cone points. Specified distance away from the cone points. So for example, if your surface looks something like this with cone points on the edges, we could take one of our SOTs to be the surface which sort of stays a certain distance away from the cone points. That'd be all this little stuff. So there's there's these subsets. When I control the diameter of the subsets, and then controlling how far away they are from the singularities. And then finally, you have this integral condition, which was
Square.
there was some stuff, and it involved the diameter of the teeth thing, and then there was this distance away from the singularities. Feel free to jump in, but there's something. And it was an integral in terms of dt, and the condition was that if this is infinite, then the flow is uniquely ergodic. So this theorem works really well in this case. We're constructing surfaces with infinite cutting and stacking things, because we can rephrase these conditions about how the geometry degenerates in terms of the dimensions of these columns, which we're cutting and stacking, or in terms of the widths and heights. So let me give you the rephrased, I'll say the application of the theorem, of Rodrigo's theorem. Gives us a theorem. I'm really running out of time. So here's the statement. Let B be a compatibly weighted Bratteli diagram, ordered, all that good stuff. And since we're only interested in flow in the vertical direction, the side identifications don't affect that. So it can be by infinite if you like. Here's the condition. Suppose for every number eta, there exists a sequence of epsilons indexed by k with epsilon k less than or equal to the minimum of these renormalized heights, h(i)k bar over 2, and renormalized widths, k bar over 2, where we take the minimum over all of the towers in the kth level, such that for, and I'm going to define some delta, which is referring to sort of, controlling the geometry, how we approach singular points. And there's another one, sigma, which is 1 plus the sum, sigma k, as I goes from 1 to the number of vertices in level vk. So it's summing over each of the towers in that level, hi k bar. We have two conditions. One, that 2 epsilon k sigma k is less or equal to eta. And 2, this is the reformulation of the integral condition, that the sum over all the different k's of epsilon k to the minus 2 sigma k plus the norm of vk, number of vertices of vk, minus 1 divided by delta k equals infinity. If those two things are satisfied, then the flow in the vertical direction of the surface is uniquely ergodic. So all we've done really is we've rephrased Rodrigo's conditions on how this geometry of the surface can degenerate, what rate it can degenerate, in terms of the heights and widths of these columns. So, look good? Yeah. Okay, there's this theorem. What's it useful for? I should show you an example. So it's useful for many things, but I'll do one particular example in my remaining 5 minutes. This theorem allows us to force this remark. These are very numerical computations. We just check how the geometry of the surface changes, the heights, the lengths, or you could program this into a computer. If this thing adds up to be infinity, we have unique ergodicity. So it's a really nice condition that's easy to check. Well, maybe not easy, but algorithmic. So an example of how to apply this, an example where this theorem applies. So I'll start with the Bratteli diagram. This is the level V0, and there's one vertex. At the next level, V1, there are P1 number of vertices. At the next level, V2, there are P2 number of vertices, so I haven't specified this yet, and so on. So we have the sequence of natural numbers, P1, P2, P3, etc. And now how do we connect? I'm going to draw some edges. I'm going to connect each edge, sorry, maybe ignore this one. I'm going to connect each edge, each vertex in this level to every vertex in the level below it. So maximally symmetric. And then I'm going to add some additional edges. I'm going to add n nk minus 1 edges between a point here and a point here for each of these points. So I'm going to add some number of additional edges. So nk, this would be the number n1 edges. The next level, we do the same thing. We connect them all up in the sort of maximal way possible. Then we add some additional edges, connecting pairs, and it's going to be nk number of edges. And the question is, given the appropriate weighting, is the corresponding surface, does the vertical flow, is it uniquely ergodic? And if we use this theorem, we get the following result. Lemma. If plus 1 cubed plus pk minus 1 nk minus 1 whole quantity squared. This quantity, so this infinite sequence of p's and n's, we sum over k. If this equals infinity, then the vertical flow on the surface is uniquely ergodic. So, Rodrigo promised an uncountable class of examples to which this theorem would apply. This is one uncountable class.
This is countable.
Sorry?
Is this uncountable?
I think this is countable.
This is okay. This is countable. I promise this is uncountably many. Okay, I haven't quite fulfilled Rodrigo's promise. There are more, and I think that's where I'm at.
Other questions?
Wait, isn't it uncountable? I mean, PK can just be randomly chosen to go between like 2 and 3. Wouldn't that give you an uncountable?
Yes.
Okay. And
There are
The-
lots of examples where it's
am I correct in presuming that the compatible weighting criteria is the same as saying that the added transformation on the graph is measure preserving?
Yes.
Yes.
In which case, if you're willing to forego measure preserving, you can talk about similar things for arbitrary Bratteli diagrams, yes?
Sure. It's just that then you lose the translation structure.
But if the end result is to say the vertical flow is uniquely ergodic, the translation structure doesn't seem to be all that important. You're just talking about the infinite interval exchange between the top and the bottom.
I mean, it's the same, I mean, systemic only changes here to the surface.
Well, right, but I mean, if we're only flowing in one direction, then
Some system would be uniquely ergodic, I guess. Well, we should talk more about it, as I said. That's a good question.
Yeah, in your last lemmas, yeah, even assume that nk is 0 for all time. How far is it from being an equivalence?
How far is it
From being an equivalence?
They have to be natural numbers.
Yes, sure. No, but
They have to be
you have an
positive
if
natural
then.
numbers,
The question is, if this is finite, do you have several measures?
So this condition is sufficient. I
Yes.
don't know if it's
No,
necessary.
I know a counterexample.
No, I don't know. Okay. What do you mean? In which direction you?
If you have just 2 vertices at every level, then this is not. Yeah, I don't know. I can tell you later.
But you have a big nk in that case, right?
Yeah.
But assume nk is 0.
Well, nk should be a positive
equal 0.
number.
This is
A natural
definitely
number.
not. Yeah, we can talk about it later.
Okay.
I was curious, you thought about looking at other directions on these surfaces?
Yeah, it's much less.
Probably.
Yeah, no, yes, we have started to think about that, and we have made some progress.
Okay. I didn't really expect that elaborate.
The answer is it's will be announced at an undefined future date.
there's some recent preprint, and I can't remember who it's by, although the list is fairly short of who it could be, but it involves ergodicity of the composition of an infinite interval exchange and or rotation, which would exactly be flowing in the other direction.
Yeah, I saw some things like that. So it allows you to put a finite interval exchange on the sides.
Yeah, that's right. If you were just imposing rotation in the interval exchange, that wouldn't account for the size of this translation structure.
Right. Yeah, it's actually it's pretty difficult. I say pretty difficult in that I've spent a little bit of time thinking about it. We both haven't really figured anything out. But for example, in the case that the ergodometer case, it works out nicely because there are cylinders, and so they twist around the cylinders, or something really Pat knows quite a bit about. But it's a little harder. Yeah. Anyway, I guess the short answer is we don't know.
Maybe just a less. Do you have any idea about what the beach groups of these objects are?
The big scoops.
The beach groups.
Beach groups.
I mean, you have a construction, and then this construction. Is there any correlation about the dynamics you see in the beach groups you see?
Well, I mean, the one immediate one is that if your Bratteli diagram is periodic, then the geodesic flow, or with the appropriate T, is an element of the beach group.
Oh, so you have all these hyperbolic elements.
Right. Right, so I guess I can even state that remark.
Okay.
If the Bratteli diagram is periodic, G sub T is in the beach group for some T. And thus, the beach group contains a copy of C.
But that's something. Okay.
And maybe more.
So we have quite a lot of topics to think about. Excursion. Yeah. Actually, again.